Hi everyone, it's nice to see you all from sunny England. I wish I was actually down there with you in Australia or New Zealand. Anyway, nice to meet you all. My name's Vincent Moulton, and I'm going to talk today a little bit about some work that I've been doing on phylogenetic networks. So what we're interested in is the problem of reconstructing phylogenetic networks from distances. So this is joint work with Leo van Iersel, Momoko Heizemiyu, Katerina Huber, and Yuki Murakami. The work is described in these two papers, which overlap a little bit, which you'll see why in a minute. And I'd like to thank the Netherlands Organisation for Scientific Research and Research Institute in Kyoto University and the London Math Society, which made it possible for us to travel and work on these problems together. So the main object of interest is a phylogenetic network. You've probably seen in other talks already what a phylogenetic network is, so I won't spend a lot of time defining these things. These are slightly different maybe from ones that people normally study because they're unrooted. So the mathematical definition for an unrooted phylogenetic network is it's a simple connected graph where all vertices have degree 1 or 3, and the leaf set of the network corresponds to a set of species. So if you're given such a phylogenetic network, you can define distances between the species, of course. Okay, so for example, here we have species A and B, and they are distance 3 apart because there's a path here of length 3 between them. Of course, here we could also look at the distance, say, between A and C, for example, and then we would see that that distance is 1, 2, 3, 4, 5, 6. Okay, of course we could go in different directions. Here we could have gone from A along here, okay, to C, but obviously that is a longer path, and we're interested in the shortest distances for the moment. So the main question that we're interested in then is if we're given, say, the distance matrix coming from a phylogenetic network. So in this simple example here, we have the distances recorded between the different species A, B, C in this matrix. Then can we reconstruct that network from that matrix of distances? Well, this is obviously, probably many of you realize this is an old question in some sense. I mean, the first problem you could think about is, well, we've got unrooted phylogenetic trees, and are those reconstructible from the distances between the leaves? And of course, we all know that's true. But actually, the fact that this was true for trees was, I think, first proved in this paper going way back to Hakimi and Yao in '65. Of course, there were others involved later on in tree reconstructibility from distances, such as Booneman, but at least let's say that it's a well-known fact that we can get back a tree from its distance uniquely. So what about unrooted networks in general? Well, it's useful to have a kind of filtration on the networks so that we can study this problem in a little bit more detail. So we could talk, what we're going to look at are level K networks. So what's a level K network? So let's begin by understanding what we mean by a blob in the network. This is a maximal 2-connected subgraph with at least 3 vertices. Okay, so in this example here of a level 2 network, we have 2 blobs. Okay, and we'll call a network level K if at most K edges must be removed from each blob to get a tree. So why is this a level 2 network? It's because we can remove this edge here, for example, and this edge here, and this edge here, and we'll get a tree. Okay, so we've removed at most 2 edges from each of the 2 blobs. So here are the blobs, and we've obtained a tree. So it's level 2. So we know that level 0 networks can be reconstructed from their distance matrices because a level 0 network is a tree. So what about level 1 networks? Well, so here's a nice example, simple example of a level 1 network with 2 blobs. And in fact, one of the results that we proved in both of the papers I mentioned is every level 1 network can be reconstructed from its distance matrix. So as with trees, it's a nice observation. We can actually, if we're given the distance matrix for a level 1 network, we can actually build it back from that distance matrix. So that's all sounding very nice. Well, at least to mathematicians who get excited about such things. But what about then level 2? We think that's hopefully that's some good news too. But actually, as Leo and Yuki and I found out, even level 2 networks are not reconstructible from their distance matrices. So you have to sort of stare at this a bit. So these are 2 level 2 networks. And if you look at the distance matrix on the set A, B, C, D, you actually get exactly the same distance matrix for both networks. But as you can probably imagine, these networks are not isomorphic. They're not the same network because, for example, this blob here with A and B and this blob here with A and B in the other network, they have one blob obviously has an edge across it and the other doesn't. So these are not going to be the same, not isomorphic networks. So we can't reconstruct level 2 networks from their distance matrices. So that might be a bit disappointing maybe. However, so we started to think about that and thought, well, what then, what would we have to know from the distances, say, to be able to get back a level 2 network, for example. Okay, so what we then started to consider are multi-sets of distances. So now we don't just look at the distance between any pair of points. Say here we've got A and B, which are distance 3 apart, say here, but we also look at the other sort of distances that we get by going in different ways between A and B. So in this example, we could, of course, go like this to between A and B, and then we get a path of length 1, 2, 3, 4, 5, 6. Okay, so then we see, oh, look, we also get another path here of length 6 between them. And in this little sort of matrix that I've drawn here, we actually have 2 paths of length 6 between A and B, which is why we've got here 6, 2 and 3, 1. That just means that the multi-set of distances between A and B is given by, well, 1 path length 3, 2 paths length 6, and the rest of the entries there reflect the multi-set of distances between the different species coming from that network. So the sort of next result, nice result, that Leo, Yuki and I were able to show is that actually if you're allowed to look at the multi-set distances coming from a level 2 network, then you can actually reconstruct the network back from its multiset distance matrix. I have to say, part of the idea for looking at multisets came from some really nice work which was kicked off by Magnus Bordrich and Charles Semple a little while ago, where they look at whether you can actually get rooted phylogenetic networks back from distances. So that's a kind of parallel story for the rooted case, and there are more papers that have come out recently on that you might find interesting if you find this area topic of interest. So that all sounds good. So then we thought, right, okay, what about level 3? And already we were able to quite quickly find, I remember sitting in the Netherlands with Yuki, Leo and Remy, and quite quickly we found that even for level 3, even if you know the multi-set of distances, you can get 2 networks that are different. Again, you can see that this blob and this blob are different. So we have 2 non-isomorphic networks which have exactly the same multi-set distances. Of course, these are rather funny looking networks. They have only 2 species. I always have a good laugh about that, because I think Danny Hewson once asked, can we get past 3 species? And apparently in this example we can't even get past 2. So at this point you think, well, what's to do next? Well, one thing that's obviously missing from these arguments, and which we normally see when we see phylogenetic trees, are edge weights. Okay, so we could actually then wonder what happens if we allow edge-weighted networks. Can we then, when we define the distances between different species now by shortest paths, where we have now to take into account the weight of the edges that we use. So I'm not going to add these up, but you can imagine now we're going to add up the edge weights of those paths to get our distance matrix. And again, we'll take the shortest distances in the first instance. Then can we get back then the network then, if we're allowed to sort of weight things? And the interesting answer, at least, is if you have weighted level 1 networks, then you can actually reconstruct them from their distance matrices. So this little piece of work was done with Yuki, Momoko and Kati, and we were able to show that you can actually even generalize the idea of a level 1 network to what's called an X-cactus, where you now allow not only that the leaves are labeled, but you can have higher degree vertices. So, you can have this vertex here, higher degree, and you can have internally labeled vertices. So an X-cactus is essentially a level 1 network, or a network where the blobs are all cycles, but where we're allowed now to have internal labels and leaves labeled. So it's a bit like the analogy of an X tree, and we can actually, in fact, if you're given even all of the edges are weighted, then you can actually reconstruct that X-cactus from its distance matrix. So that's a nice situation. Of course, the next case you might then wonder is what happens when we get to level 2. But we've already seen, for shortest path distances at least, that we can't reconstruct even level 2 networks which have only edge weight 1 on every edge. What's interesting is when you get to level 2 and you allow edge weights, things can get even a little bit more nasty. So this example here was even presented in a really interesting paper going back to Althofer in 1988. So here we have an example of what we would call a sort of an X level 2 network, where now we've got species A, B, C, F, E, and D. The distance the distances between these species is given by taking, again, shortest paths. And you see that we've got a level 2 network now because we have to remove 2 edges to get a tree, okay? And if you take a stare at this, then and you look at the distance matrix that you get on the set A through F, then it's exactly the same for every epsilon lying between 0.5 and minus 0.5. So that means that not only then do we have the problem that there's more than one network representing exactly the same distance matrix, but in fact we have an infinite family of networks with exactly the same distance matrix. Of course, this isn't the case when we look at level 2, where we only allow edge weights 1 because we have sort of a countable number, well, a finite number of possible networks there. So indeed, it seems for the weighted case at least, things can get really quite complicated. So, you know, just to conclude then, hopefully this is a rather short talk, which I hope would be quite nice. What are the future directions? Well, we could ask, can we actually characterize networks, whichever kind they are, level K, etc., that are reconstructible from their distance matrices? So we know that some are reconstructible, some are not. Can we actually characterize some other ones that are reconstructible? And possibly more interestingly for phylogenetics, are there nice efficient algorithms to reconstruct networks from distances? And even if we can't do that exactly, a bit like with, say, neighbor joining, we can build trees back using neighbor joining. So are there ways, for example, to build back X-cactuses from messy data using a kind of similar algorithm? So that's it. Thank you very much for your attention. I appear to have gone over by a few minutes. I'm sorry about that, but I hope you enjoyed that talk, and it's been nice to be able to join Philomania, even though only virtually. So, bye-bye.